All right, so our first step is going to be breaking the cable up into 1 meter discretized sections. Now, it doesn't have to be always have to be 1 meter, but 1 meter is a good starting point for a bridge that's at least 40 meters. And this allows us to um, model that still preserve some of that parabolic shape. If we were to use too large of sections here, you'll notice that as we're calculating the change in distance or the change in total length of the cable, we would lose some of that granularity and we would not get as close with our custom sag predictions. So we've set up our discretized sections of cable, our linear segments, and we also need to establish some sort of coordinate system or starting point, our XY, so that we can plot the values and plot the locations of each of these points and how they'll move. This is just for the purpose of if you're doing this in Excel or a computer program, you want to have a solid coordinate system that you can use to relate everything, because typing in everything by hand is going to take a very long time, so you want to be able to do it with formulas. So we take these linear segments and we can then set up little force triangles and use a squared plus b squared equals c squared to get the distance and change in distance, as well as the tension in each segment of cable. And remember that our pH, our horizontal tension, always remains the same across the entire cable length. So once we set up our points and we know that our horizontal tension is the same across all points, we can use that to calculate our cable tension. And we can use that to calculate our cable elongation of each little individual segment. And you may notice that the horizontal tension pH comes from the sag value. We can't calculate this without a sag value. So we'll need to start by initializing the problem and making a guess at this sag value, so that we have values to start, and then we'll go back and we'll iterate to find the right sag values that make these sides of the equation match. So we'll set this up for our hoisting. We'll set this up for our dead load. And we'll set this up for our live load geometries. And remember, these are going to be based on a guessed sag value for hoisting and live load. And then once we have this guessed sag value and we've set up our coordinate systems and our force triangles, we can then calculate two things. One, the cumulative distance. So we can sum all of the small delta x values here for each segment, and we can find the geometric elongation, so the amount that the cable as a whole in discretized 1 meter sections is going to extend and stretch. And then we can also calculate a p average value by taking a average tension in each segment. And that will be important for later when we plug this into our equation for force elongation. So finally, we can come through to our equation I presented before. We have our geometric elongation, which is going to be our L total, which I've put down here. That's going to be the cumulative distance that the cable stretches, minus our L naught, which is going to be just our span at that geometry. So, sorry, it won't be our span. It will be our cable length from previous geometry. So this is going to be either our change in cable length from hoisting to design or our change in cable length from our live load to design, right? So because we're predicting those two sags based on our guess of design sag. And then we can also do the same for our force elongation, plug that P average term in, and that's going to be our change in force from hoisting to design or live load to design to see how much the cable stretches, and we can iterate to solve for our sag value.